Okay. So, in this lecture we will be focusing mostly on problems, and we will have a very brief discussion on if we have some time towards the end, we will have a discussion on calculus of variation. But for first let us start with the problem. Okay. So, I have as usual this small problem set prepared for the class. Whichever we have covered so far in the class will be discussed in this problem set. Okay. So, we will start with the simple problem of Atwood's machine, and the question is we have to find out the equation of motion. Basically, solve the problem means finding equation of motion. First we have to use D'Alembert's principle, and then we have to use Lagrange's equation of first kind to solve this simple system. So, Atwood's machine is essentially this 2 mass 1 pulley system, okay, which is very familiar to all of you, and we will look it up. Okay. So, the first problem A, we have the Atwood's machine, which is one mass m1, the other mass m2, right. Now, first, okay, let us assume, we can assume some radius a for this pulley. Okay. So, we can take the center. There is a reference line at the center from where we measure all the heights. This is the reference line. So, this is my displacement of the first mass, displacement of the second mass. Okay. What is the constraint here? First of all, let us identify the constraint. The constraint is the length of this thread. This is in Atwood machine, it has been assumed that there is no friction in the pulley. We are very familiar with this frictionless pulley assumption, right. So, this is one assumption. The second assumption is the total length of this thread is constant. So, it is not a stretchable string. So, if we write down the constraint equation, so L will be equal to x1 plus x2 plus pi times A. Okay. Now, you can might as well just avoid writing pi times A, because we will see towards the end that it will not contribute unless and until we are. So, also we are assuming that this is massless. If this is massless, writing this pi A will not affect anything. If we consider that the system has mass, then we have to take the angular momentum into or the rotational energy of this into account, then this will have some effect. But anyway, right now we are considering that there are only 2 masses in the system, m1 and m2, and this is massless. Okay. The pulley is massless, string is also massless. Okay. So, in terms of D'Alembert's principle, how do we write it? D'Alembert's principle, if you recall, we have to get the forces. The force on the first mass is m1g, this is m2g. So, if we write, it will be mx double x1 double dot minus m1 x1 double dot minus m1g delta x1 plus m2 x2 double dot minus m2g delta x2, okay, which will be equal to 0. So, this is precisely our D'Alembert's principle, one equation, single equation. And as I said already, and you also must have realized that this single equation is useless unless and until we use the constraint equation. So, basically we cannot do much from here. Now, from the constraint equation, we can immediately just take a virtual displacement and say delta x1 is equal to minus delta x2, is not it? Definitely it is. It has to be, I mean, delta x1 plus delta x2 equal to 0. Take a derivative of this and it will come out. Substitute it here. So, what do we need to do is we need to put a minus sign here. Okay. You can get rid of this delta x1, put a minus sign, put a bracket, put this delta x1 outside. That is it. So, you use this relation. When you get this, you start, when you get it in one, okay, there is a delta x2 also, which also has to be merged with delta x1. So, this is the case. If this is the case, then the double dot will also be replaced, has to be replaced. No? So, you do that. So, you get m1 plus m2 x1 double dot minus g common take it m1. So, it will be minus minus plus minus m2 delta x1 equal to 0, right. And now, because there is only one coefficient of delta x1, so the whole thing can be equated to 0. So, we can get rid of this delta x1 as well, right. So, we can put this equal to 0, which gives you x1 double dot is equal to g m1 minus m2 divided by m1 plus m2. Okay, that is it. And this is your very familiar form. If you have a simple Poulier mass system, this will be the acceleration. Okay. So, if one acceleration is, and this symbol means there is a minus sign between derivative of x1 and derivative of x2, that essentially means if the velocity, one mass is dominating, then it will come down this way. If mass 2 is dominating, then it will come down this way. Okay. So, this is all included in this calculation in the final form. So, you just have to put the values of m1 and m2, and then you will get whichever way, whether x1 is positive or not. Okay. So, this is one way of solving it. The same equation we can solve by so this was by this what you call D'Alembert's principle. Now, the same equation has to be solved by Lagrange's undetermined Lagrange's equation of first kind, which is like including this constraint condition explicitly, and including this constraint means once again the constraint can be written as delta x1 is or plus delta x2 is equal to 0. So, we have to multiply a lambda for each of this with this constraint condition. So, it will be lambda delta x1 plus delta x2, and then we have to separate, we can separate it out into delta x, variation in x1 and variation in x2 form. So, if we do that, we will get m1 x double dot minus m1 g, and it will be, oh sorry, you do not have to do this, you do not have to do this. So, your phi, okay, so your phi is x1 plus x2 plus phi a minus L equal to 0. So, this is your equation. Okay. So, what you need to do is, okay, so what you need to do is lambda del, so this essentially this is your phi of x1 and x2. Okay. So, it will be del phi del x1 and lambda del phi del x2. Now, it so happened that these are all both are first order. So, this is simply equal to lambda, and this is also simply equal to lambda, right. So, you get 1 and you have m2 x2 double dot minus m2 g plus lambda equal to 0. Okay. So, once again we got now we have two separate equations in two parameters, but again we have to do some trick. The trick is now we subtract one from the other. Okay. So, once we do that, we get rid of these lambdas, lambda cancel out. So, what we have and once again from the constraint condition we see that x1 double dot is equal to minus x2 double dot, because if we take a derivative of this, it will be the just opposite. So, if we do that, once again we get x1 double dot is equal to m1 plus m2, and on this side of course we will have m1 or rather minus m1 minus m2. So, you put a equal sign instead of writing it 0. So, once again you get x1 double dot is equal to g m1 minus m2 by m1 plus m2. So, it is little more simpler as expected compared to D'Alembert's principle. It is little more simpler. We get two separate equations, simple algebraic manipulation, and of course, we have to keep in mind here also we need to use that x1 double dot is equal to minus x2 double dot. Okay. And then finally, we got this equation. So, I just took a very simple example of Atour's machine in order to demonstrate how this two techniques work, but please remember both these techniques are a bit primitive in nature, in a sense that they really need serious algebraic operations to go to the final equation. Also, we are good here because we have only one constraint condition. If we have more than one constraint condition, it will be a not so easy job, right. So, this is the first problem we did, but again this is a good practice. I mean, Atour's machine is a very good model system to study very simple kinetics. It is good to learn these techniques anyway. I promise to give you little more slightly variation, I mean slightly different problems in your assignments, and I hope you will enjoy them. Okay, so let us move to the next problem. A particle of mass m is projected with initial velocity u at an angle alpha with the horizontal. Use Lagrange's equation of motion to describe the motion of the projectile, neglecting air resistance. So, essentially we are just what we need to do is we need to simply write the Lagrangian of a system of a projectile and see if we can get to the equation of motion. So, it is very straightforward. Now, we have finished Lagrange's equation of first kind, we have finished Lagrange's equation, D'Alembert's principle and Lagrange's equation of first kind. Now, it is the Euler-Lagrange equation or Lagrange's equation of second kind. So, a projectile which is fired from ground, so this is my x axis and this is my z axis, okay, which is fired from ground with an initial angle, okay, so maybe it is going something like this. So, the initial angle was alpha and at any point the velocity v is given by x dot square plus y dot square, or rather z dot square. How many parameters do we need? Generalized parameters. We need two generalized parameters, because a free particle, as I discussed in the last one of the previous lectures, is a free particle needs 3 degrees of freedom. Now, moment we are projecting this particle as a projectile, we are throwing this particle in the air as a projectile, we are making it stay in this yz plane. We have to realize that. So, it is not a free particle anymore, it has certain constraint. Now, thankfully, we do not have to take this constraint into account because we are dealing with Lagrangian. Now, but we have to choose the generalized parameters. So, we need two generalized parameters which we have to choose wisely. We might as well take r theta, we can take this as the origin O, any arbitrary position, this is r, and we can take this theta. This is also a very valid choice of generalized coordinate. I suggest so let us do it this way. I will do it with z and x and z or Cartesian. You will take a polar coordinate, do it yourself. It will be a good practice. Okay. So, kinetic energy T is given by half m v square, which will be x dot square plus z dot square. Now, if I write the same thing in polar coordinate, what will that be? Equal to half m r dot square plus r square theta dot square, is not it? So, we can write this, we can do that. I suggest you build up on this one, right. And V, which is the potential energy, is given by m g y, right, clear. So, the total Lagrangian L is half m x, or sorry not y, z, x dot square plus z dot square minus m g z. Any cyclic coordinate? Yes, x. There is no x explicitly in this expression. Okay. So, z is not a cyclic coordinate, but x is a cyclic coordinate. Typically, kinetic energy, we will see that in most common case is kinetic energy has only velocities. Okay. So, we will have, for example, here we have x dots and z dots. Very rarely we will see that kinetic energy term contains, at least in this particular going to the next few lectures, whichever example we will take, you will hardly ever see that kinetic energy is a function of coordinate also. Of course, there will be cases when we will be discussing small oscillation, we will be seeing cases where kinetic energy can be potentially a function of coordinate, but right now let us not do it. So, this is one, and we have, so typically the coordinates, not the velocities, but generalized coordinate come in the potential energy part. Now, in this potential energy part you do not see a coordinate, most likely it is a cyclic one. Of course, it is a close inspection. I mean, why I am saying this, because sometimes the Lagrangian of a system could be so big that you might miss one or two terms in between. So, if you have to check for cyclic coordinate, my suggestion would be check the potential energy part first. Okay. So, equation of motion will be damn simple, d dt of del L. So, there will be two equations, one for x and one. So, let us start with the x equation first. So, del L del x dot minus del L del x equal to 0. So, there is no dissipation forces present. Okay. We have not included air resistance. So, right now we have a 0 here. So, if we do that, we have m x double dot is equal to 0. Okay. Cyclic coordinate, or rather m x double dot is equal to 0, which means m v x equal to a constant, which is obvious because in projectile the x velocity has a constant value, and from the starting point itself we know that this will be, if your initial velocity is v, then v x will be v cos alpha, is not it. So, we immediately see that v cos alpha is equal to constant, right. And then we have potential energy, right, sorry, for the second equation y, it will be d dt of del L del, oh sorry, not y again, sorry, z dot minus del L del z equal to 0. So, it will be m z double dot, it will be equal to, or rather minus m g. Okay. So, it will be a plus sign here because there is a minus here, there is a minus here. So, it will be a plus sign here. So, which means z double dot is equal to minus g, which is absolutely fine. This is how the equation of projectile looks like. Okay. So, initial angle, if we want to solve this, we will need to use explicitly the values of the initial angles and all. Otherwise, just to get to the equation, this few one or two steps are good enough. Right. Now, so second problem is solved. Let us move to third problem. Third problem is a particle of mass m moves on a plane in the field of force given by F is equal to minus k r cos theta r cap, where k is a constant and r cap is the radial unit vector. Will the angular momentum of the particle about the origin be conserved? Justify your answer, and then we have to obtain the equation of orbit for this particle. Okay. So, we are given with a force field F, which is minus k r cos theta r cap. Okay. So, we can write this as F r or minus F r r cap, right. Now, we have to construct, and it is a 2D motion which is already specified. It is a motion in a plane, it is already specified in the problem. So, we can write velocity v, or rather the magnitude of velocity v square to be equal to r dot square plus r square theta dot square, right. Okay. So, yeah. So, kinetic energy T is equal to half m r dot square plus r square theta dot square. By the way, in the previous problem, if we have a dissipation, for example, a viscous damping, it will be a good practice if you can just add a Rayleigh function with the Lagrangian and take the write the final equation. Okay, that will be a good practice for you. Please do that. Okay. Here now we have to write V. What is V? That is the question. V is the potential energy, and please remember that F is del V del R. F R is equal to minus del V del R. Okay. So, I will just write it here. So, F R is equal to minus del V del R, which is given by if we just write the expression of F, which will give us, or rather this is F R, not minus. So, the minus sign will be included in here. So, we will get K R cos theta, right. Now, because it is a partial derivative, the form of V can be predicted directly, and please remember that total force is given in terms of only one component. So, there is no, so we can assume that del V del theta is equal to 0, which is a valid assumption because there is no force in the theta direction, right. So, if we do that, if we integrate this, we will get half k r square cos theta, right. So, V is equal to half k r square cos theta, very good. Now, that means the Lagrangian L will be half m r dot square plus r square theta dot square minus half k r square cos theta. Okay. So, this is the Lagrangian. Now, we have to check for what was it? Yeah, will the angular momentum be conserved? So, the force is pretty much like a central force. Whatever force field is given, it is also a radial force. So, in a radial force, we have seen that in central orbit, that for a force which has kind of similar nature, the angular momentum vector has been constant. Will it be the case here? The answer is no, because if you recall, angular momentum was the total angular momentum was that was conserved looking at the Lagrangian. I mean, from a Lagrangian perspective, what we have seen that because L, so yeah, so because Lagrangian does not contain theta explicitly. So, what we had was del L del theta dot is equal to a constant, which was exactly m r square theta dot for a central orbit. But in this case, the Lagrangian has a function of theta. So, in this case, del L del theta dot will not be a constant. So, that way this force field whichever is given, although it is radial in nature, because of this theta dependence over here, it is not a true central force. Please keep that in mind, that a force could be radial, it does not matter. A force could be radial, but it is not a true central force unless and until your the total canonical canonical momentum associated with the angle theta is a constant, which is not the case here. Okay. So, we can now we have justified part A. So, part A is over. Now, for part B, we have to find out the equation of motions. Equation of motion, there will be one R equation, which will be, so you have to follow the same routine. Once again, ddt of, so ddt of del L del R dot minus del L del R is equal to 0. Once again there is no dissipation present here, so it will be 0 and there is no another additional constraint forces. So, it is all included here, and the second equation will be similar equation for theta. So, I am not doing it, you can finish it yourself, and it is pretty straightforward. Okay, fine. Okay, so problem number 3 is, sorry, it was problem number 3, not 2. Problem number 3 is over. Now 4. Okay, so we have a problem 4, one problem 5. Let's start with problem 5. Now, in the during our discussion on generalized coordinate, I have said many times that generalized coordinates need not have the dimensions of coordinate. It need not be lengths, need not be angles. It could be anything. I mean, it could be any other quantity. So, this is an example where we have given with an LCR circuit, which is something which is very common for us. Okay, and we identify. So, what we need to do is we need to write a Lagrangian for this system. Also, we have to find out dissipation. Assuming that the dissipation is proportional to current, we have to write down the Rayleigh function. First of all, before we do anything, we have to identify a generalized coordinate associated with this system. Now, it turns out that charge, electric charge which is moving through this circuit can very well satisfy the criteria for a generalized coordinate. Okay. Now, let us look at this problem. So, we are doing problem 5. We have a system of R and L and C present, and there is a current moving. Okay. So, the current in the system, let us call it I, which is a function of time. So, it is changing with time, and there is a drive E which is also a function of time. This thing we have not discussed so far. I will tell you now. I will tell you how to, if we have a driving force on top of everything. For example, if we have a forced harmonic oscillation where there is a driving force constantly driving, periodic driving force which is constantly driving a system, how to take that into account. Okay, I will discuss this now. Okay, so now first thing is we have to identify the sources of kinetic energy. I mean the terms corresponding to kinetic energy and potential energy. Now, if you look carefully, we are all familiar with the basic operations of this component. What happens moment you close the circuit? For now, let us assume that there is no driving here. What we have, maybe there was a battery, okay, and there was a switch, and the switch is closed at time t equal to 0. As and when the switch is closed, there will be a charge flowing in this circuit, and that is why charge q has been taken as the generalized coordinate, because it is the most fundamental quantity. We can write I t as q dot. So, I, the current, serves the purpose of a, so I will put it here. I is the generalized velocity in this case, and q is the generalized coordinate. Okay. Now, as the charge goes through this circuit, what happens is the capacitor charged up. Okay. I mean, it will accumulate a charge difference, some finite charge difference, let us call it q. So, we are all familiar with the relation that C is equal to q by V. So, whatever the voltage difference V here, that according to that certain charge q will be accumulated, but that is the final step, the steady state solution. Now, in between what happens is this, before you reach a final value, this q will also be a function of time. Now, as the charge build up, there is a potential energy building up into the system. So, capacitor is the source of potential energy. So, whatever energy is stored in the capacitor is potential, I mean, is like a potential energy, okay, energy stored in C. Now, on the other hand, L, what is the effect of inductance in a circuit where there is either no current or where is a steady current, where there is a steady current flowing? The answer is 0. There is no effect. Okay, I can write out the different terms of I can the the fundamental frequency dependent terms for this, each of these, and try to show you, but that is not strictly needed. Even if you do not want to go into all this, the basic concept is very simple. An inductor will only participate, I mean, inductor will acquire energy if and only if there is a charge flowing through it which is changing as a function of temperature, or current flowing through it which is changing as a function of temperature, right. If there is nothing flowing, nothing will happen. For a DC circuit, a steady state DC circuit, an inductor is nothing. Whatever resistor it has, resistance it has, only that has some effect, otherwise it will not change. But in an AC circuit, because the current is a time varying function, the inductor has a finite effect. Okay. So, because it is related to the dynamism of the system, dynamism as in when the current is changing as a function of time, only then this comes into account. So, kinetic energy is the energy stored in L. Okay. And it so happens that energy stored in C is half C V square, and this is half L I square, okay, where L is the I is the Q. So, what we can write is, instead of I, we can write Q dot square half C, and for the first term, it is half C V square. Yeah. So, now what we can do is, we can bring it in form of charge, and we can write half Q square by C, right. So, we have a potential energy which is equivalent to half Q square by C, and a kinetic energy which is proportional to, which is equal to half L Q dot square. So, the total Lagrangian L will be half L Q dot square minus half Q square by C. But that is not all, we have a Rayleigh function, and there is a hint given that you have to take assuming that the dissipation is proportional to the current, write a Rayleigh function. So, the dissipation is proportional to current means it is like velocity dependent viscous damping. So, we might as well write the Rayleigh function as write it here, f equal to half r I square, okay, and I is nothing but Q dot. So, it is half r Q dot square. Okay. So, for the equation of motion, we have only one generalized coordinate, and we have a Rayleigh function, a Lagrangian. So, for the equation of motion, we have to do d dt of del L del Q dot minus del L del Q, okay, plus del F del Q dot is equal to 0, right, for this particular system. And if we do that, we will find for the first two terms, it will be L Q double dot, right, minus 1 by 2 C Q minus plus R Q dot R Q dot, right, R I, which will be equal to 0. Now, this is when we have a battery in the system, and the the switch is closed at t equal to 0. But if we have a driving force in the system, even after driving force is something or rather E driving potential, this is something which cannot be included in the Lagrangian at any form. But what we can do is, see, when we are writing this equation of motion, we are bringing it down. This is in the dimension of energy and these are in the dimension of forces. Okay. So, what we can do is we can, if we have some force which cannot be considered in as a force of constraint, which cannot be included in the external forces or rather which is an external force which cannot be included in the force of constraints or dissipation forces, what we do is we put it on the right hand side of this equation. Okay. So, your final equation is just like this. Now, if we instead of writing q dot, if we write I, how does this equation look like? This equation will look like L I or rather I will just write it in long notation just to make it look little familiar. So, it will be L d I dt minus, oh sorry, it will be already a minus here. So, it will be a plus sign here. Okay. So, it will be plus 1 by 2 c integral I dt plus R I equal to E of t. Now, if any of you are familiar with PID control, this is the proportional term, this is the integral term and this is the derivative term. So, this three, so basically what we have written is the PID equation of an LCS circuit here. Okay. So, I hope it makes sense. In order to also, if we have more complicated circuits, if we have one more compartment here, for example, we have additional resistor and this, we can assume that there is another, so let us call it Q1, there will be another charge Q2 circulating in that loop and we can might as well write an equation for that. Also, you have to keep in mind that Q1 and Q2 are not entirely independent, but they are related by Kirchhoff's current law and voltage law. Okay. We can find examples of such things in different literatures which I have mentioned, also you can find in the internet and you will definitely find these things. Okay. So, I think today we will stop here. In the next class, we will start with the last problem, that is problem number 4 of the set, which is once again a problem which we have partially discussed in the class, but now we are running out of time currently. So, what I will do is we will start with problem number 4 in the next class and then we will continue our discussion and we will start a new topic called calculus of variation. Thank you.